Hello everyone, I'm Zhang. I will present the work AdaCheck, an adaptive checkpointing system for efficient large language model training with redundancy utilization on behalf of the authors. Large language models have demonstrated impressive performance across various intelligence tasks. Due to their extensive parameter and data size, large-scale distributed training has become the standard training recipe of large language models. In this mode, models are iteratively trained on hundreds or even thousands of workers. During training, model states are distributed to occur according to the adopted parallelism. We show the distribution of model states when training with state parallelism and model parallelism on two workers respectively. In training, these two parallelisms are combined for use. This combination introduces complex state redundancy. State redundancy defined as the duplication of model states resulting from parallelism, model architectures and training iterations impacts the volume of data processed and the number of communication operations required per iteration during training, thereby affecting the performance of distributed training. Large-scale and lengthy training is coupled with failures. For instance, the 54-day training of Llama 3.1 on 16,000 GPU encounters 419 failures, with training failing on average every 3 hours. And the optimodal training reports a failure frequency of twice a day. The core of failure recovery is checkpointing, which periodically seeks model state checkpoints, enabling the resumption of training progress from the latest checkpoint. However, checkpointing techniques used during large language model training lead to a notable waste of training resources. According to the relevant technical reports, about 2 million GPU hours are wasted during the training of Llama 3.1, and about 178,000 GPU hours are wasted during the training of Opti 175 billion model. To reduce the waste of training resources caused by checkpointing, existing checkpointing systems have optimized the checkpoint storage process. For example, checkframe decouples the checkpoint offloading process to remote storage from the training loop and restricts the checkpoint saving to only rank 0 workers, enhancing checkpointing performance under data parallelism. Meanwhile, Gemini improves network bandwidth during checkpoint storage by offloading checkpoints to CPU memory, thereby enabling higher checkpointing frequency and achieving performance gains under 0-3 parallelism. However, these offline approaches are limited to specific parallelism or model architectures. Moreover, we observe that state redundancy also exists during model training iterations. Existing checkpointing system overlook this redundancy, thereby missing the opportunity to leverage it for checkpointing performance improvement. And based on the limitations of existing checkpointing systems, we propose AdaCheck, whose primary goal is to build an adaptive checkpointing system that achieves a minimized checkpoint size by characterizing state redundancy across various parallelism model architecture and training iterations. To achieve this goal, AdaCheck must address several key challenges, the first of which is complex state redundancy. This complexity arises from the diverse combinations of parallelism and model architectures. Model states are typically composed of model parameter and their corresponding optimizer states. During checkpointing, both must be safe to ensure recoverability. As shown in the figure under the same parallelism, the state redundancy of a given model parameter and its optimizer state may be identical or differ under different parallelism. The state redundancy of a given model parameter and its optimizer state can vary significantly. To analyze this intricate state redundancy, we propose an offline redundancy utilization method. This method realistically considers the state redundancy of mode parameter and their optimizer states when constructing checkpoints. Besides, this method effectively reduces the checkpoint size by leveraging the state redundancy in parallelism and model architectures. It is first necessary to obtain fine-grained state redundancy. However, existing checkpoint systems are unable to capture such fine-grained state redundancy. This figure shows the checkpoint storage behavior of current checkpointing system when using 0-1 for parallel training. Lazy executed checkpointing methods generate checkpoints only after failure occur. This approach neglects model states without redundancy in the faulted worker, resulting in unsuccessful training reception. Remote storage checkpointing method need to save at least one complete model to remote storage, incurring significant overhead. And remote in-memory checkpointing organize workers into groups, allowing each worker to save its checkpoint in the CPU memory of all other workers in the same group. This decentralized design enables checkpointing over faster intra-group connections, but results in the unnecessary saving of redundant model states among workers. To address this, we introduce the concept of tensor redundancy and aim to analyze model state redundancy at the tensor level. Based on the offline redundancy utilization method, we can reduce checkpoint size. However, tests show that relying solely on this method is insufficient to achieve one step, one checkpoint, or 1C, which is the optimal checkpoint frequency for checkpointing. In the figure, we present the network bandwidth required by different methods to enable 1S1C when training GPT 18.4 billion and Llama 7 billion on 32 GPUs under various parallelism. Here, AdaCheck employs only the offline redundancy utilization method. We observe two key findings. First, training systems can improve performance by utilizing more GPU memory. And for example, switching from 0.3 to 0.1 or enhance downstream task performance through specification techniques. However, both strategies increase the network bandwidth demand for achieving 1S1C. Second, the network bandwidth required by an existing checkpointing system to support 1S1C is often unattainable in practice. The persistent storage bandwidth used by PyTorch naive checkpointing and checkfree is typically under 100 gigabits per second, while the worker interconnect bandwidth used by Gemini and AdaCheck is generally below 400 gigabits per second. To address this limitation, we propose a method that reduces checkpoint size by leveraging state redundancy across training iterations. And based on the opportunity identified above, we propose AdaCheck, which consists of three components. First, an offline redundancy utilization method that introduces the concept of tensor redundancy. And it models the state redundancy inherent in parallelism and model architecture and selects appropriate model states to generate reduced checkpoints. To efficiently identify tensor redundancy, we design a tensor redundancy detector. Finally, we propose an online redundancy utilization method that reduces checkpoint size by leveraging a state redundancy across training iterations. We first introduced the offline redundancy utilization method to capture the state redundancy introduced by parallelism and model architecture. We propose the concept of tensor redundancy, which formally describes the distribution of redundancy, redundant tensor replicas across devices during parallel training. Since model states consist of one or more tensors, we can derive the state redundancy based on tensor redundancy. In AdaCheck, we classify state redundancy into 3 types: full redundancy, partial redundancy, and no redundancy. And considering that the state redundancy model parameter and their corresponding optimizer states may differ, and given that both must be preserved to ensure checkpoint usability, we compute the intersection of state redundancy between parameter and their optimizer states. This intersection determines whether a parameter and optimizer state pair should be included in the checkpoint. For example, if the intersection yields no redundancy, both the parameter and its optimizer state are stored in the checkpoint. To efficiently obtain tensor redundancy, we propose a tensor redundancy detector. This detector first hashes the value of each tensor, then aggregates all hash values from a device into a packed tensor. This tensor is exchanged among devices to determine tensor redundancy. To accelerate this comparison process, we implement 2 optimizations. First, comparisons are performed only among devices with the same communication group. Second, a ring-based communication algorithm is applied to reduce redundant comparisons. As shown in the figure below, when comparing using the ring-based algorithm in the right half with a communication group size of 4, all pairwise tensor redundancy results are computed in the first half of steps. In the second half, instead of transmitting the packed tensor, devices directly propagate the already computed tensor redundancy results, eliminating redundant comparison and accelerating the overall process. And next is the online redundancy utilization method. We observe that change in model states across training iterations are driven by gradients. This insight leads us to the idea of storing only gradients in mixed precision training, storing half precision gradient instead of model parameter and their optimizer states dramatically reduces checkpoint size. Built on this, we propose a gradient-based incremental checkpointing method. In this method, gradients are offloaded to remote CPU memory, and a CPU-based optimizer updates model parameter remotely, thereby reducing the data transfer overhead during recovery. And in the experimental setup, we use both a data center GPU cluster and a commodity GPU cluster. We evaluate 6 state-of-the-art models covering both dense and sparse architecture. We select check-free and Gemini as our baseline methods. Experimental results show that compared to other methods, AdaCheck reduces checkpoint size by 600 to 896 times. And AdaCheck enables 1S1C checkpointing frequency, significantly improving the performance of checkpointing systems. And for more details, including time complexity and analysis of redundancy detector state redundancy with auto-generated parallelism and proof of the recovery probability, please refer to the paper. In summary, this work addresses 2 key limitations of existing checkpointing system. Based on these limitations, the key idea of this work is utilizing state redundancy across parallelism model architectures and training iterations to reduce checkpoint size and improve checkpointing frequency. To achieve this target, we developed AdaCheck, which comprises 3 core components: an offline redundancy utilization method, a tensor redundancy detector, and an offline redundancy utilization method. Experiment demonstrates that AdaCheck significantly reduces checkpoint size. Okay, thanks for your attention. Please feel free to contact Weijie Liu via email if you have any question. Thank you.